Thank you. So first, I would like to thank the organizers, Sergei and Natasha, for the invitation to be here in this wonderful place and in this wonderful conference. I realized also that I was a little bit optimistic when I wrote the abstract, and I thought I would talk about both. Yes, voila. I thought I would talk both about capacitance and Hall effect, but this was probably too difficult to do in the about half an hour that I have. So I decided to recenter the talk on the Hall effect. And as you will see, this is more a plea to experimentalists to find new systems, new ways of probing the kind of physics that I think is very interesting, and I'll try to challenge you by showing what another community was able to do. So let me first show the people who did the work. So the thing on low density systems was done mostly by Giacomo Morpurgo, who is a very talented graduate student in the group, and in collaboration with Luc Rademacher and Christophe Berthaud. I'll show also all the data that we obtained together with Christophe Berthaud and Gladys Léon on the Hall effect. And a good part of some, I would say, unusual effects for the Hall effect in interacting system were obtained in collaboration with these various people, Sébastien Grechner, Michele Filippone, Cécile Repellin, and we have some analytical results with Edmond Rignac and Roberta Citro, and I'll hopefully have time also to present some works on triangular ladders with Katalin Alati. And we were very lucky to collaborate with the wonderful group of Leo Falani, and Tianwei Zhu was the person at the head of the experimental efforts, where you will see that one can measure Hall effect in cold atomic gases. And, I think condensed matter should raise up to the challenge and have equivalent data. Okay, so Hall effect, you all know what the Hall effect is, but let me just remind Hall effect 101. You take a piece of material, you put a magnetic field, you pass a current, and you measure the Hall voltage in the direction perpendicular to the current. And for non-interacting materials, this is a particularly simple thing. And what you will find in every textbook in condensed matter is that the Hall resistance, which is the transverse voltage divided by the current divided by the magnetic field. Here I will not go to very large magnetic fields, so I'm not worrying about Hall quantizations and whatever, is essentially 1 over the number of carriers. That's an exercise you can give to your first solid state physics course, and that's essentially always wrong. Despite the fact that most experimentalists believe that it's correct. No, they are not that naive, but they kind of use this as a measure usually of the number of carriers. So when there are no interactions, we know now that the physics is extremely rich. And actually what the Hall resistance measure is an integral of the curvature of the Fermi surface. There is a very famous formula, which is called the Thouless-Komoto formula, which relates the Hall effect to a topological invariant. That was a good part of the Nobel Prize of David Thouless, actually. And essentially, you have all these wonderful things. You know that if you raise the magnetic field, you can get the integer quantum Hall effect and so on and so forth. But to cut a long story short, as soon as there are interactions, the Hall effect is an open question. So I don't know anybody who has an efficient formula to compute or even to relate to quantities, except, of course, the basic Kubo formula, which is able to give you what the Hall resistance is for a system and interaction. And in high TC in particular, I think the blood is still drying on the walls of the conference where people discussed Hall effects as well as theories of high TC, but in particular Hall effect. Okay, so I would like to discuss in some cases what we can say with for interacting systems. And I will cover two interesting situations. You know, the definition of something interesting is something on which you worked. So that's my definition. So there will be the case of low density systems. I think this is probably the most appropriate for this audience because this is something that has been used a lot in 2D materials, and I'm really new and peripheral in this field, so I'm learning a lot at this conference. But this is something we looked at, so I will discuss the Hall effect near an empty band. And then there is a second situation that has actually been an old obsession of mine, which is what happens if you try to do Hall effect in a system where interactions are reinforced by the dimensionality of the material, namely coupling one-dimensional chains, and you will see that this is a complicated situation. So let me briefly go first to low density systems. Of course, I will not dare at this conference mention all the wonderful 2D materials that one can create and one can dope by using typically gating. You heard the wonderful talk of Shahar on the first day of the conference. I'll show here data which is coming from the group of Alberto Morpurgo. The reference will pop up in one moment, where they were liquid gating 2D materials here, which you have below, and depending on the voltage that was applied to the liquid gate, of course you could populate the band, and then you measured very strong changes in the conductance of the material. So there is an interesting problem associated with the liquid gating, and it's a little bit mentioned in the abstract, but I won't discuss it in details during this talk, is that all the classical, I would say, formula, when I say classical, I mean including quantum corrections, of the capacitance that were given in the literatures are essentially incorrect, or rather incomplete. And in order to describe this liquid gating, we need to consider not only the terms that were considered in the capacitance, namely that the capacitance is fixed by the classical capacitance, you know, two plates separated by a distance L, by a quantum correction which takes into account the fact that each electrode is itself a quantum system with a Fermi potential and so on. But there is a cross term that is only important if the two electrodes are very, very close to each other, because each one is influencing the potential of the other, and you need to take this correction if you want to be able to describe this type of curve. So this is something we did in these two references. The first one is mostly experimental and corresponds to data that was taken in the group of Alberto Morpurgo. And the second is more, let's say, theory-oriented, with all the diagrams that explain what this last term is, and is mostly due to the efforts of Christophe Berthaud, in the thing. So there is a crossover scale, which indeed corresponds a little bit to the criterion you've given, but with a little twist. But absolutely, when you start putting the electrodes, let's say, closer than a screening length, which is associated to the distance between carriers, you need to take into account this third. Okay, so let me forget about the capacitance, but consider this type of system, and now consider that I am extremely close to the bottom of the band, so I will have density of carriers which are very, very small, and the question is, if you measure the Hall effect in such system, what will you see? And this is something we looked at, as I said, with Giacomo Morpogo, Luc Rademacher, and Christophe Berthaud. And of course, we used standard derivations of the whole resistance, which is the conductivity, which connects the fluctuations of current along X and Y, normalized by the conductivity along X and conductivity along Y. So this is a well-established formula. And under certain circumstances, for theorists, if you neglect the vertex corrections, you can relatively exactly rewrite these two components as a function of the spectral function, which is the probability to find an excitation of momentum k and energy epsilon in the system. And of course, the chemical potential controls the number of carriers. And of course, the question is, you have to give yourself a form for the spectral function. And we choose here to deal with spectral functions that are essentially k-independent, and to look a little bit at what it would give. So let me give you two examples. The first one is to consider a constant self-energy, a constant so not the spectral function, but the scattering time is essentially a constant, and it gives a Lorentzian form for the spectral function. And here is the Hall effect plotted in color code here, normalized by the, I would say, standard value, the 1 over n. And so when it's deep blue, it means that the Hall effect is indeed 1 over n. And when there is a color which is different, it's not 1 over n. And you see that if you assume that there is a finite scattering rate, impurities or other objects, when you will deplete the band, you go through something which is essentially the canonical value of the Hall effect. You are close to the bottom of the band, so the spherical Fermi surface is a very good approximation and so on. But nevertheless, you go through a regime where the Hall effect is considerably reinforced compared to the naive value. And then when you deplete very strongly, you go to a regime where you're still with 1 over n, but with a coefficient 4. So I think one should be extremely careful by in identifying the Hall effect with just 1 over the number of carrier, even if one is close to the bottom of a band. Yes?
How is the scattering rate compared with the Fermi energy? Do you have Fermi liquid here?
So here we don't have interactions. The self-energy is the only one in the system. So you could say we have a Fermi liquid, and then on the top of this we put this self-energy. But by definition, when we're here, the Fermi level is small compared to the scattering rate. No, I'm perfectly happy with that. We are not in a regime of Landau Fermi liquid, but I'm just cautioning the fact that one has to be careful in identifying 1 over n with the Hall effect. I'll show another example, which is because you could say, indeed, this is a little bit brutal. You took something which is a constant, and the Fermi level is going to 0. We can take a Paolo for the self-energy. This is the imaginary part of the self-energy. This is typically what you would get with impurities by doing self-consistent Born approximation on impurities, or by taking interaction with phonons or something like this. And lo and behold, when you do the same analysis, what you find is, again, that when the density is reasonable, you find that you're in the deep blue here, so you're at a Hall effect which is given by 1 over n. You note that you get this reinforcement here of the Hall effect, which is present, but now because we put a Paolo, you can also get values of the Hall effect which are even smaller than 1, with a coefficient which is smaller than 1. So I think it would be extremely interesting to have measurements on these materials very close to the bottom of the band. The difficulty is to know what is n. Usually, people take n as given by the Hall effect, which is, of course, not optimal if you believe this graph, but it would be interesting to try to see, indeed, what type of physics is coming on. Note that here I'm still at density where I assume that the electron gas is a liquid. I'm far from Wigner crystallization or other system like this. Yes?
If you had a situation
So actually here, I didn't detail it, but with a self-energy which is of this form, you can pull in the gap below the band, you can pull a perfectly sharp bound state, which would be the equivalent of an excitonic bound state and whatever. And some of the features that are observed here are a consequence of this excitonic bound state. So again, we are playing at the moment because, of course, solving completely the problem is extremely complicated. As Shahar said, well, if you don't get a Fermi liquid, you sit and cry, essentially. But at least this shows that one should be extremely careful. Although you could imagine that close again to the bottom of a band, you get essentially a nice circular Fermi surface. Yes? No. So here, no. So here, except for this power law, which is the result of the self-consistent Born approximation, if we put impurities, this is what you will get. The rest, we inject the self-energy. But you're right, there should be much more sophisticated treatments which are performed in this regime. Okay, I'll stop here for this part. And I want now to go to what is a little bit the bulk of the talk, which is what happens if I try to look at coupled one-dimensional structures. Why this? Well, first, I love one-dimensional systems. The second thing is that in one dimension, interactions are an essential feature of the physics. Try to go through the line when you will queue for the lunch, and you will realize that you cannot, because you have interactions with a person in front of you, if you try to move, you will transform your individual motion into a collective motion. The whole line will have to move with you. So in 1D, even a small interaction drastically changes the physics of the problem. So this is a problem that has been around for a long time because there were compounds, the organic conductors, the so-called Beshgard salts, which are actually very nice coupled 1D structures. One has more recently examples in the cold atomic world. And after listening to the beautiful talk of Shahar and seeing that you can do whatever flat band you want with a moiré, I dream of the fact that maybe by using a moiré, one could have a good bandwidth in one direction and a small bandwidth in the perpendicular direction, and maybe that would be an alternative of realizing a 2D array of coupled one-dimensional structures. So let me show you experiments on the so-called Beshgard salts, which, as you see, are chains which are plunging in the direction of the screen. So the motion is with a hopping which is about 3,000 Kelvin in the direction of the chain. Then let's say 200 K in the perpendicular, in one of the perpendicular direction, and 20 K in the third direction. So this is in first approximation systems made of 2D planes of 1D coupled chains. Now, you would think measuring the Hall effect is fantastically easy. You put a magnetic field perpendicular, you pass a current along the chains, and these compounds are super clean. You pass a current along the chain, and then you measure the voltage perpendicular to the thing. And indeed, it was measured. There is a measurement done by Joël Moser in the group of Denis Jérôme in Orsay, and not the date. This is 25 years ago, essentially. And you see a very strong temperature dependence of the Hall effect. So you say, haha, I have an interacting system and it's a strong temperature dependence of the Hall effect. And then you have a measure which is made on the same compound, not the same sample, but the same compound, in the group of Laszlo Foro at EPFL. The two papers were published back-to-back in PRL, also 25 years ago. And this one has a completely flat temperature dependence of the Hall effect. Since then, nobody has remeasured. Nobody has measured in another compound. So I cannot tell you which one of these two experiments, maybe both, is incorrect. So hear me, it would be nice to have a measurement of the Hall effect in something which is made of coupled one-dimensional chains, because maybe there is something to understand there. And I have my favorite, of course, of the two curves, because I will show you what we have for theory, but the ball is in the air. And it has been in the air since 25 years. So, why is it complicated, or why is it interesting on the theoretical side? Okay, doesn't want to move anymore. Oh, I understand. It has took, voilà. So, no. Voilà. Why is it complicated? It's something we looked at together with Antoine Georges a long time ago, and André Lopatin. Naively, you have 1D chains, and we have very good theories for 1D chains. It's called Tomonaga-Oettinger liquid theory, and so we know how to deal with interactions in 1D chains. So normally, what you would like to write is the kinetic energy of the 1D chains. You would like to write the interaction term in the 1D chain, the perpendicular tunneling in which you put the gauge field which is responsible for the magnetic field. And as I said, we have an excellent way of treating this type of problem. The problem is that if you just do this, you will find zero for the Hall effect. And you will find zero because if you take a strictly linear spectrum, which is the usual Tomonaga-Oettinger liquid description of 1D system, you impose an artificial particle-Hall symmetry, which is not present in the real problem. And when you have particle-Hall symmetry, the Hall effect is zero. So you need to add a term here, which is describing the curvature of the dispersion. And if you don't do it, you get zero. But when you do it, your very nice method, which allowed you to solve with using Tomonaga-Oettinger liquid theory, it collapses as well. Not completely, but it becomes a nightmare. It becomes a nightmare because you have to expand in this curvature, you have to expand in this transverse hopping, you have to expand in the magnetic field because you want to do this, and this is complicated. So nobody was really able to do it seriously. So we started to do it non-seriously, meaning with whatever technique we could do. And this is what we did with Gladys Léon and Christophe Berthaud, which is to use a method which has been pioneered by Götz and Wölfle, which is also known as Mori formalism, which is so-called memory matrix, memory function, but which for the Hall effect has to become a memory matrix, which is a glorified perturbation analysis. And when you do this, this is what we found. We found that in these materials, the Hall effect normalized to the naive classical value, by classical I mean non-interacting particles value, is essentially with a correction, so it's RH0 minus a correction which is a power law of the temperature with an exponent which depends on the interactions in the system. This parameter K is the so-called Tomonaga-Oettinger liquid. Yeah, R0 is proportional to the curvature, absolutely, yeah. That's what you would get with free electrons, no interaction, so it's proportional to alpha. Okay, so this is what we get, and then this theory becomes invalid at the temperature where the material stops to be weakly coupled 1D chains and become seriously a 2D material, which is another problem in itself. It's called dimensional crossover. But this is a perturbative result, and we hope it's correct. That's why I was saying we have a favorite on the two curves. I much prefer this curve than the flat one, but okay. We cannot guarantee either the theory or the experiment. So this is a complicated situation, and that's why it would be highly desirable, now that there are many materials which are really 2D and on which one can perhaps control one of the direction, to repeat this type of Hall measurement. Yes, Charles? So then the dimensional crossover climbs at the level of the cutoff here of our theory, and we're always unable to do the calculation. So in order to do this kind of perturbative calculation where we expand in T-perp, we need T-perp to be small compared to T-parallel to have a window in which we can consider the system as weakly coupled 1D chains. And this crossover temperature for the real material is around 150 Kelvin. Knowing that most transport measurements stop at 300 K, this doesn't give a very large window. So it would also be desirable to have a broader window. There are optical measurements of the normal transport, which are already much more favorable because now the cutoff is 3000 Kelvin. And then you can, and 150 Kelvin is 150 centimeter minus 1. So for the conductivity, there are beautiful measurements which show the power law behavior associated to Tomonaga-Luttinger liquid. To the best of my knowledge, there is no corresponding curve for the finite frequency Hall effect. That would be nice also. I turn towards our chairman for this. Okay. So let me just to show that we have not been lazy in the last whatever 20, not 20 years, but let's say 17 years. We've turned to simpler geometries. We've turned to simpler geometries, and we said if we cannot solve many coupled chains coupled to each other, let's solve two. Let's do a ladder. So let me take one chain here, one chain there, tunneling between the chains, and interactions along the chains, and so on and so forth. And maybe with two, we are able to say things. And indeed, we are. And the motivation was that this system exists. They don't exist in condensed matter. I mean, there are some ladder realization in condensed matter, but not from really metallic system. But they exist in cold atoms. So let me just show you, without entering into details, a system which was realized in Leo Falani's group. They use actually an internal degree of freedom of the atoms as a kind of thing which tells on which chain the atoms are. So this is physically a single chain, but morally, you can view it as three different chains, because by using Raman pulses, you can make transition between the state m equal minus 5 half to m equal minus 1 half and whatever. And moreover, every time you do such a transition, you can impose a phase. And if you impose a phase, you put a gauge field, which will be the equivalent of putting a magnetic field. So they can realize a perfect ladder, here a three-leg ladder, together with a magnetic field that would, atoms are neutral, so normally a real magnetic field would not do anything, but this phase is creating this pseudo-magnetic field. That's why they call this synthetic dimension and synthetic gauge field. So by using synthetic dimensions and synthetic gauge field, one can get ladders, and moreover, they can put a kick, and the kick is passing a current, which they can measure, and they can measure the imbalance of population, and therefore they can measure the Hall effect. Here are corresponding experiments done in the group of Jan Spielmann in Maryland, where essentially they have a five-leg ladder, and you can see here the drift of a particle, so if you want under the Lorentz force, going from one edge to the next edge. Okay, so question is, what happens with the Hall effect on ladders? And this is something we looked at first numerically with Sebastian Grechner and Michele Filippone, and I just show you here the data. So we give a kick to the ladder to impose a current which is passing. So you see the current depends on time. We measure the imbalance of population. You see the imbalance of population depends on time, but the ratio between the two converges very rapidly to a plateau, and this plateau is the whole voltage, it's the whole resistance. Actually, I'm a little bit lying to you here, but it's not important. And so we can compute this, okay, lost my cursor. So we can compute this thing. What is remarkable is that we found numerically that there is a universal value of the Hall resistance. I'm not talking about quantized Hall, small field. If the interactions become large enough, we recover 1 over n for the whole resistance. So this is weird, because I tried first to convince you that 1 over n never works, but I'm just telling, now you take a system in which 1 over n doesn't work for non-interacting, but now you crank up interaction, and you recover 1 over n for an interacting problem. And so, can we test? And the answer is yes. So this was done in collaboration, as I said, with a group of Leo Falani. So here is the system. It's a 2-leg ladder. This is the artistic view, but this is real data. This is the momentum distribution. So you see there is a kick. There is much more particle with positive momentum than negative momentum. So it means there is a current passing. And this is the difference in population. So it means there are more particle on this chain than on this chain. And when you do this, you can measure the current, you can measure the imbalance, you can do the ratio, which sort of goes to the plateau, and you can check that indeed, let me show the interaction result, you can check that indeed this whole imbalance goes to the universal value, which corresponds to a whole resistance of 1 over n. So, yep.
These atoms, are they fermions or bosons?
So these ones are fermions. But you can do the calculation for bosons, for fermions, doesn't change in this regime. So the interaction is, again, we can do in the simulation on-site, or so here the interaction is actually along the rung, because this is the same site. So this is a rung interaction, but it doesn't change the existence of this plateau as far as the MRG, the numerics, is telling us. So these are not changing this result. Okay, my time is shortening, so let me just finish with one last thing, which is very recently, together with Edmond Rignac and Roberta Citro, and this is more for maybe theorists, we managed, by using this Tomonaga-Luttinger liquid theory that I was mentioning, including the curvature term, to compute the whole resistance. And this was a little bit painful calculation, complicated one, but the formula at the end is so simple and so beautiful that I'm sure there is a better way to derive it. What we find is that the whole resistance is the derivative with respect to the density of particles of a certain product of the Tomonaga-Luttinger parameters, but this product has a very simple signification. That's the weight of the Drude peak. That's so-called cone stiffness. So we have a kind of magic relation between two transport coefficients, the stiffness, which tells you how your conductivity in the absence of magnetic field is able to transport current, so the Drude weight, and the whole resistance, and one is simply the derivative with respect to density of the other one. This is what comes out of the calculation. It has consequences. For a Galilean invariant system, we recover the 1 over n, 1 over rho. And for a system which is close to a Mott transition, we do recover that the whole resistance is diverging as the distance to the Mott transition. So this formula has nice feature, and it would be interesting again to compare. So we are now trying to compare with numerical simulations, but it would be interesting to have measurements. So the compressibility is actually the ratio of these two. So this is another quantity. It's not the compressibility. This is also dangerously close to something called the Streda formula, which has been used for Hall effect, but in a regime with gaps. Here we are at small fields. There are no gaps. So that's why I'm saying there is probably an intelligent way of deriving this formula, but I don't know it. Okay. Just to flash one last thing, if you try to put now frustration in the hopping, and this is what Katalin did by looking at triangular ladders, you have a very interesting phase diagram, but the only thing I want to show is that the Hall effect is a very, very good signature of the phase transitions that exist in this system. Here is the Hall effect. And you can see that when we go from one phase to the next, which is signaled by these lines, the Hall effect is having the kind of divergence that I was mentioning before. So it seems that Hall effect into interacting materials, we start to understand them a little bit, but it would be fantastic to have additional experiments on other systems than the ones that exist at the moment to try to help a little bit with this. So on this, let me conclude. I think the two take-home message is that at low density, there is an anomalous behavior of the Hall effect, even for parabolic bands. And for the ladders, we have this universal regime, which gives us back the 1/n, but for large interactions, which is a little bit surprising. This is confirmed in experiment in cold atomic gases, at least for two-leg ladders. And we have now a simple analytic expression that would need further verification. So on this, I think the message is we need experiments on the condensed matter side. And on that, I'll stop and thank you for your attention.